All right, welcome everybody. In this video, I want to continue our exploring of vector spaces and subspaces in particular. And so we've been looking at subspaces and really focusing more on subspaces of vector spaces which consist of vectors. So we've looked at R4 and looked at a subset of R4. We've looked at a subset of R3 to determine whether it is a subspace. Since we've dealt with vector spaces of more abstract things, let's revisit subspaces in these more abstract realms. So for example, we've already taken a look at a vector space of polynomials that had at most degree 2 with our usual operations, and we verified that that set and those operations satisfy the axioms for a vector space. If I let V denote the set of all polynomials, right, of any degree, and we have the usual operations of how we add functions and how I would multiply a function by a scalar, then let's consider a subset of V that we denote H, which is the set of polynomials where the coefficients are all integers. So for example, I could have a function f of x which looks like 3.5 x squared plus e squared x minus the natural log of 2, right? And this is a polynomial because we have some number times x squared plus some other number times x plus some constant term. So what makes it a polynomial is that the powers of x, right, occur to positive integers. And these coefficients here are certainly not integers. So this would be an element in the set V, which is not in the subset H. So we're restricting ourselves now to just thinking about polynomials where each of the coefficients is an integer. So things that look like this. So we want to check, is this a subspace? Does it satisfy these three conditions? So is the zero vector in here? So inside of V, the zero vector is the polynomial 0, right? And so here, if I add this function to any other polynomial, right, we are not going to change the value of that polynomial, so we get the same polynomial back. And this we could write as 0 times x to the n plus 0 times x to the n minus 1, 0x plus 0, right? So this is a polynomial where all of the coefficients are 0, and 0 is an integer, so this polynomial has all integer coefficients. So the 0 vector, which is kind of like the 0 function, is indeed included in our subset H. Is it closed under addition? Yes, it is, right? Since if we add any two integers, the result is an integer. Therefore, when we add two polynomials, we add them by their degrees, right? We group like terms together. So if each polynomial f and g has integer coefficients, then their sum f plus g is going to have integer coefficients. So that works out just fine. What about scalar multiplication? So let's pick a particular function. So let's say I have f of x is equal to 3x squared, as I have above, plus 2x minus 5. This is inside of H. And I'm going to pick a scalar c, which I'll pick to be 1/2. Now let's see what happens if I take c times f of x. So I'm going to take 1/2 times 3x squared plus 2x minus 5, and this gives me 3/2 x squared plus x minus 5/2. And the issue here is the coefficients now are no longer integers. So this is not in H. So this is not a subspace. And we have 2 out of these 3 conditions that work out. The issue is here it needs to be closed under scalar multiplication. And this will work for some scalars, right? As long as I pick a scalar which is an integer, will be okay, but it doesn't work for all scalars. So this is a property that needs to work for all scalars, and property 2 needs to work for any two vectors that I pick in our set. So again, the issue is not property 1 or property 2, but it's the third property that does not pass. So this is not closed under multiplication by a scalar, so this is not a subspace. Okay, so let's take a look at another example dealing with functions. So we previously took a look at a vector space V that consisted of all continuous functions from the real numbers into the real numbers. So all like single variable continuous functions with the usual operations. So with the usual scalar multiplication and the usual addition. We did look at an example where we defined addition as composition of functions, and that actually wasn't a vector space. So we're going to assume we've got continuous functions with our nice operations. So V is a vector space. And we're going to consider the set H of all differentiable functions. So H is a subset of V because if a function is differentiable, it has to be continuous. Okay, but not all continuous functions are differentiable. So here we're taking the subset H, which is just the subset of V of all differentiable functions with our usual operations. And now we want to think about whether this is a subspace of the vector space of all continuous functions. So is the 0 vector inside of this space? So here the 0 vector is the function that is 0, right? Since we want to make sure that for any continuous function, when we add this vector to it, this function, right, we should get back f of x back. So our 0 vector in V is the 0 function. And then is this a differentiable function? Yes. This function z of x is differentiable. Its derivative is equal to 0. So since this is differentiable, we have the 0 vector in our subset H. Is it closed under addition? So if I have f and g, these are in H. So these are both differentiable functions. Is it true that if I take the sum of these two functions, can I take the derivative of the sum? And we know that this is a really nice property that derivatives have, right? That we can distribute the derivative through sums. So yes, if f and g are both differentiable, then the sum f plus g is also differentiable. And thirdly, if I take some scalar c times f of x, is that going to be differentiable? And yes, it will, because I can pull out the constant and then take the derivative, and I know that f is differentiable since it lives inside of H, so this exists. So here is a pretty nice subspace. If I consider the original vector space as all continuous functions from R to R, then this subset H, which is just the differentiable functions, they actually form a subspace. It satisfies these three conditions.